today we'll talk about hybrid brain computer interfaces. Here on the screen you can see the main points of my presentation. First I will remind you what brain computer interface is, then we will switch to the gaze-based interaction, and after I will present my current research, which consists of 3 different studies. So first of all, what is brain computer interface? It's such technique which allows us to communicate with the external environment without using muscles. It can be used for the robotic control, for the medicine purposes, or for gaming industry. The main problem of the brain computer interfaces is their low accuracy. The alternative method which can be used for the same purposes as BCI is the gaze-based interaction, when we can detect gestures and long fixations and use them for robotic control and so on. So the limitation of this method is Medachta's problem, that we cannot get rid of the gestures which serve our vision, and also sometimes it's complicated visual task which can cause epilepsy and something like that. Also, this technique sometimes costs really a lot. So what we can do? We can combine them together and try to create a hybrid brain-computer interface which will solve our problems. There are many different hybrid brain-computer interfaces, but all of them have their own limitations. In our lab in the University, we tried to create our model of hybrid brain-computer interface to solve some of them. Here you can see the main paradigm which we used for our BCI. So firstly, person looked to the rest area, then fixating the stimulus, counted flashes, made a saccade to the certain direction, fixate to the stimulus for one more time, and go to the rest area. The aim of our study was to find such psychophysiological elements of hybrid brain-computer interfaces which will work in the real life for the robotic control. So we accept electrodes for EEG and 4 electrodes for EEG recording. First study was to evaluate amplitude of event-related potentials in the multiple stimuli P300-based paradigm. Here on the screen you can see how the stimulus area looks like. So this was the stable part where chapters were presented, and this part flashing all the time like in P300 BCI. This suggests that such interface will give us complex arrangement of the stimulus, many possible comment for each stimulus, and also that it will give us high accuracy because of EEG and EEG. Here at the screen you can see how it works. So a person looks in the rest area, then move his gaze to the target stimulus, count 4 flashes, look up, then back to the stimulus and back to the rest area. Results were so that for different positions we have different ERP results. So you can see that in some cases we can see N1 component, and in other we cannot see nothing. So that's why we decided not to investigate this method and change it a bit. Also, we think that maintain 9 stimulus of the mobile robot, it's quite hard, and every time flashing stimulus is quite a complicated task for the users. That's why we perform another experiment where we compare different variants of the stimulus color to obtain the most stable, pronounced, and high amplitude EEG response. The task was that participants sit in front of the stimulus in the distance of 1.5, 3, and 5 meters, and it was the rest area, just white cylinder, and this is it was the target stimulus which flashes all the time. So in this part we decided to choose these colors and also use just lamp which blinking like in white color. So first you look at the white cylinder, then move gaze to the target stimulus, count for its flashes, make saccade to the certain direction, go back to the rest area, and then all repeat. Result was so that for black and white stimulus we obtain more pronounced and high amplitude event-related potential than in the situation with the colored stimulus. According to this, we decided that it's better to use black and white stimulus into other part of the experiment. So the field study was to compare different variants of the stimulus and choose the best one and also evaluate dependence of event-related potentials from the distance between the user and the stimulus. So the procedure was pretty the same, but in this case we use regular and random circuits like an example of the stimulus. So the procedure was to look at the rest area, then move gaze, count flashes, and go back. So the individual result was that we can see in different participants quite pronounced high amplitude event-related potentials. We can see P1 and one EP2 component in most users. That's why we decided to use those components in the statistical analysis. So here you can see the grand average ERP for all group participants for regular circuits. So you can see that it's really pattern which we can observe. There is no such response in the condition when Korsun don't count our stimulus. So move to the statistical analysis. There is no any significant differences between the distance stimulus or effect of factor interaction was observed for N1 amplitude, for N1 latency. The only one significant thing which were observed is the stimulus factor and channels and distance interaction for the B1 amplitude. For another components, we cannot observe nothing special. So, according to this, we can conclude that we model such hybrid brain-computer interface, which allows us to test mobile robotic control in the offline. Yeah, also we obtain sustained P1 and 1 and P2 components in the occipital areas in response to the target stimulus. Also, no effect on distance and stimulus were observed for our components, but interaction of distance factors with the EG for P7 and 8 was slightly significant only for P1 component. And also, stimulus pattern consists of random circles was associated with the high amplitude of the P1 component. The aim of the further study is to record data experiment with the online classification and with the mobile robot, but this is what I'm working now in our lab, and for now I can't say nothing about this. So I want to say many thanks to my comment to Saccades, who helped me a lot today, Evgeny Svirin, Evgeny Minichuk, Evgeny Nushtin, who helped me with the programmer and the math part of my work, and to the Vigasina Christina and Anastasia Fedorova, who helped me with the theoretical part of my work. So thank you for your attention.